Hi everyone, thank you so much for joining. I think we can start right now. If anyone was attending our last stream, welcome back. If you're here for the first time, thank you so much for joining. My name is Anya. I'm a business development manager of Kmine. If you haven't already, please follow our LinkedIn page where we post our announcements for future streams. And before we start, on behalf of Kema, and I'm expressing our sincere condolences to British people in case anyone is joining us from the UK. All right, so today we talk about mineral resource validation and how it can be done in Kmine. Let's go over our agenda today. We will cover not only some validation aspects of the geological model in general, but also the resource categories. We will see what methods exist overall for analyzing the reliability of the model and estimating mineral resources of different categories. And of course, the big question is how to evaluate this reliability in quantitative terms. Also, we will review the most common methods of model validation and demonstrate examples of validating a 3D resource model in Kmine. And in the end, we will talk with our engineers about the practical application of this validation in real use cases. All right, so just to remind everyone about the packages that Kmine has, today we built 12 models for open pit and underground mining. Each of this model was created based on the real use case of a company we worked with, and each of these models keep expanding with additional features, calculation methods, and tools. Our engineers not only set up the whole company infrastructure during the implementation of our solution, but will also assist our clients at any stage of work, creating 3D models, planning schedules, estimating resources and reserves. Additionally, we offer custom add-ons that can enhance each of these models with additional tools for getting information from dispatch or fleet management system, drilling machines, and other hardware that captures data in real time. Besides, we offer custom integration with ERP systems that allow you to combine management and design tools, or really any other external information system that would allow us to receive information and import it in our application. Each of these 12 models can be used as a standalone module or used in conjunction with each other, so each company can actually pick its own set of models covering its own specific workflow. So, talking about mineral resource validation, let's start with Herbert Hoover. He was one of the first ones who proposed to divide the resources according to the degree of the geological reliability back in 1909. The approach he developed became the basis for modern classifications. According to Hoover, resources are divided into proved, probable, and possible. However, independently from Hoover in 1910, at one of the congresses, it was proposed to designate these categories in the letters A, B, C. Later, there were drafted 6 categories, and each of them had established permissible maximum error in the quantity of mineral resources. For example, A1 plus minus 10%, A2 plus minus 20%, B1 plus minus 30%, B2 plus minus 50%. And later on, these boundaries also changed. But at the same time, in the United States, Australia, European countries, the Hoover approach to classification of mineral resources continued its development. And the category of resources and reserves tells us about reliability of assessment, reliability of estimation, and risks. And there was a turning point in the assessment of promising areas of the deposit when everyone tried to unify the concept of category of mineral resources and reserves in the classification systems of various countries, but also developed transition documents or bridging documents. And since 1994, the CRISC organization has worked to create a set of standards, a standard international definition for reporting mineral resources and mineral reserves based on the evolving JORC codes definition. What's interesting, though, is one of the most common codes, the JORC code, does not specify the confidence levels. At the same time, it gives a clear definition of the concept of categories of mineral resources and reserves. Some other professional organizations rely on the stages of the project and offer quantitative expressions of the estimation accuracy range by each stage. Later, we will review current approaches to quantifying the reliability of the resource model and methods for verifying it. As for the polygonal methods for estimation reserves and the reserves, many people still use them in many countries today when they compile a report on mineral resource and reserves. However, all attempts to distribute categories of resources according to the degree of reliability turn out to be useless, because the fact is the reliability of the initial data, like sampling or chemical analysis, does not change for various categories of resources. Therefore, when estimating resources, it's almost impossible to prematurely specify a set error value for individual categories. So as a result, it was decided to assign resources to a certain category depending on the density of exploration grid. So for each group of deposits, there were established the distances between the intersections of ore bodies with workings for various categories of resources. And it was done according to the complexity of the geological structure and according to the structural and morphological types of ore bodies. In some countries, the category of exploration of resources, ABCP, still characterizes the degree of geological exploration, and the same information is carried by the G-axis on the UNFC 3D reserve and resource classification model. Generally, geologists use three methods for quantitative evaluation of estimation validation. And the first one is the thinning method of exploration grid, where the resources are defined by the densest exploration grid. That piece would be taken as a basis. Then the grid has to be rarefied by determining at each density the error in the measuring resources by comparing them with previously estimated ones. This way, the thinning methods of the exploration grids evaluates the impact of the errors of determining the resources only on the density of the grid without accounting for the influence of all other factors like morphology of the reservoir, testing errors, methods of interpreting exploration data, methods of estimating resources, and so on. And similar to the measured resource validity principle, if we drill more holes, we still get the same result. That confirms the geological and grade continuity. The other way to validate the results is to estimate resources using several methods. For example, method of horizontal and vertical sections, and then you can compare the results. And we know that the reliability of estimated resources depends on the number of ore intersections involved in the estimation of polygonal methods without creating block models of deposits. The results of the resource estimation using the method of geological blocks or vertical sections are directly dependent on the determination of average thickness values and quality indicators for ore intersections. Errors in the estimation of average block contents of useful components relate to the separate counting blocks. These errors depend on the variability of the quality of the mineral, the number of exploration sections, the density and location of the exploration grid, the geometry of the samples, and the geometry of the counting blocks. The geometrization errors depend on the morphological features of the deposit and on the density of the exploration grid, and they are functionally related to the thickness of the deposit and the degree of discontinuity of the structure, but do not depend on the number of the exploration sections. As being said, they're not functionally related to the errors in the estimation of average block grades. So if you create a model of the deposit, even if you do it without creating a block model, but only using a set of vectorized geological plans and section, and you use GIS technologies for that, you can avoid geometrization errors because of the visualization and spatial referencing. You can achieve the accuracy of the deposit's geological model by fully clarifying the or localizing elements of the geological structure and their spatial correlation. That would exclude the possibility of the other interpretations of the geological structure. And the last but not least, the validation is a comparison. The last but not least, the method of validation is a comparison of resource estimation results with operational data. Downside of this method is that it is possible only at the operational stage. However, it allows us to quantify the error of calculations in certain area of the deposit or block, and sometimes we can create a benchmark for evaluation. So we should estimate resources based on the results of only explorational data and compare it with a model based on the operational data. And if you use a traditional approach of resource estimation without applying any technology or mathematical model of the deposit, it's quite difficult to establish the reliability of geological interpretation in numbers. And there are special programs for statistical and geostatistical processing of exploration data, but their main disadvantage is that the ability to operate only with tabular data without special coordinate reference or visualization of calculation results. So that's where software like K-Mine is useful. Today, people usually assess resources using mathematical, statistical, or geostatistical methods, evaluating the accuracy of the estimation. This method takes into account contouring and resource estimation options and the errors of all variable parameters like errors in determining thickness, content, and so on. K-Mine can integrate the entire deposit data area into a single space for detailed analysis and improve the accuracy of the interpretation of the geological structure, especially in the detail areas between exploration intersections. So using geostatistical analysis in K-Mine, you can calculate quantitative and qualitative indicators using various mathematical algorithms. The calculation of grade in block models can be performed by any interpolator methods like the nearest sample method or method of inverse distance weight or Kriging methods. And you can also do a comparative analysis of the results among themselves or with the results of traditional counting. And as we already know, the accuracy and reliability of the resource estimation can be determined mainly by geological knowledge and exploration data. So they depend much less on polygonal counting methods. However, the geological interpretations are always less accurate than mathematical calculations. And since the task of geostatistical analysis is to study the patterns of distribution of elements based on autocorrelation, this helps in addition to correctly estimate resources and in numbers and to determine the reliability of the assessment. Calculation of classes or categories of resources is performed simultaneously with content interpolation. And at the same time, the class code depends on the dimensional coefficient of the search ellipsoid. That is usually determined at the stage of semivariogram analysis, as well as on the number of samples included in the ellipsoid or its sector. The validation of the resource estimation is based on the parameters of the search ellipsoid. And with a decrease in the search radius, the reliability of calculation and the category of mineral resources increases. On the basis of the block model of the deposit, in addition to a general estimation of the amount of metal, it is possible to predict amount of resource that is actually will be extracted from the subsoil. So using our pit optimizer model, you can create a final pit All calculations can be performed under various manning scenarios or with various cut-off grade options to select the optimal model options. And in Chemine, you can get a more comprehensive approach to mineral resource estimation if you use a multivariate analysis of the components and a systematic approach in research. For example, a block model can simultaneously contain information on technological types according to the processing method, technological grades, and in terms of enrichment indicators and industrial grades of ore that are outlined according to specified conditions. The best modeling results are provided when the model parameters like radius of influence or anisotropy, type, and coefficients of kriging equations or other smoothing procedures are selected by comparing the results of model calculations with the results of operational exploration for worked at areas of deposits. However, we should not forget that there are situations when the application of geostatistical methods is not possible. Resource estimation is a model that relies on large amounts of data and also on human judgment and interpretation. That means that the data information that is used to produce a resources estimation are subject to different level of quality control and validation. In terms of error, there are that are directly associated with the production of a 3D block model. It is not always possible to quantify the model uncertainty. This is particularly true for models produced using traditional estimation methods like triangular methods. So let's see an example of a deposit with rare earth zirconium ores. The ore zones are filled with altered cyanides, granites, and gracens. Because of the metasomatic genesis of the ore, we do not have a clear lithological control. So the delineation of ore bodies was performed using the results of sampling in drill holes and ditches. So let's take a small area, a database for this area. Verification of the resource model most often begins with the verification of the database and its comparison with the original materials. The same applies to digitized geological maps and the sections if we use historical data on paper. We need to make sure that no critical errors were made during the creation of the database. When creating a block model, we use solids of ore bodies, and the contouring was done based on the plans and sections which were compiled using additional data like gamma neutron logging, X-ray diffraction analysis, spectral analysis, and so on. For validation of global and local estimates, we should ensure that the final resource block model is consistent with the primary data such as the geology and mineralization, wireframe models, structural models, topography, excavation surfaces, and volumes. It also should be consistent with the analytical data that were used to prepare estimates of the modeled attributes. There are several validation methods. One of them is visual inspection in a section plan when you compare the block model grade distribution to the original drill hole and other sample grades. If you compare the volume estimates between, you can also compare the volume estimates between the block model and the three-dimensional wireframe models. Another method is comparison of primary estimated block grades, which would be based on the results of using alternative estimation methods. You can also check for global bias by estimation paths, by domain, by resource category, or comparing interpolated and nearest neighbor or the clustered composite statistics. The other validation method can be creation of Swath plots, comparing the block grade distribution to the sample grade distribution along the coordinate lines and elevation. You can also just compare it with the previous mineral resource estimation or use global summary statistics comparing the composite grades to the block grades. The method of interpolation of grades and blocks, or the inverse distance weight method, was used because the density of exploration grid is not enough to identify patterns of mass anisotropy. The analysis of variegrams showed that it's impossible to use the sample kriging, and correct calculations depend on the thorough study of the geological structure of the deposit and the correct interpretation of the results of this study. The flaws of geological documentation and the geological research cannot be compensated by any of the methods of resource estimation, really, or software, no matter how good it is. So any qualified estimation of resources should be based on fully fledged geological exploration material, and this material should be determined. This material should determine the structure of the deposit area, the morphology and the internal structure of bodies of mineral, as well as their petrographic, mineralogical, chemical composition, and technological properties. This method of comparing the average content in composite samples with evaluation in blocks along with the specified direction is pretty descriptive. It evaluates block grade errors caused by the selected interpolation method. In the video, we compare in the north-south direction in the block grades calculated by the nearest neighbor and inverse power distances with composite samples. If we need to, we can limit the boundaries of the zone coordinates for drift analysis, and we specify in the step or number of intervals on the chart. So if there are significant discrepancies in the curve of the graph, we need to pay attention to the sector and understand the cause of these discrepancies. This method of assessing the accuracy of resource calculation is convenient when you use a block model of the deposit, and it allows you to perform an express analysis of any area or deposit as a whole, both in extension and depth. Visual comparison parameters in blocks with drill holes is especially convenient with the help of the block model section in any specified direction. If it's not an orthogonal direction, you need to create a line and select settings to render necessary block model attributes. Once you visualize these parameters, you can estimate with greater degree of reliability and efficiency and increase efficiency of resource management and contribute to the improvement of the quality control at the enterprise. You can also set the visualization of markers and colors of the chart and save the chart in a PNG file, or you can export it to CSV format. The chart takes an average grade over the set intervals in a specific direction, and alternatively, the block grades was estimated using two different estimation methods. It may be compared to identify differences that were created using the different estimation techniques. These graphs only show averages over intervals and not the local block grade estimates. In mining projects, one of the recognized stages in all existing quality standards is the sensitivity analysis that is applied to the grade-tonnage relationship. In a technical report on the mining investment viability project, the sensitivity analysis refers to the curves or functions that relate to the average grade with the tonnage to the different cutoff grades. All this refers to a mineral deposit that is evaluated. Although the grade-tonnage curve is important for most economic assessments, let's remember that the model does not consider the continuity between blocks, and the approximation of the grade-tonnage curve to reality depends on the natural parameters such as geology and geochemistry, as well as geometric distribution of the deposit. Usually, the more variable the grades are, the more complex the geometry is, and the less reliable the curve is. And it's important to select the optimum cutoff referred to the grade-tonnage curve distribution, because it will successfully accompany the mining project throughout its operation. Where it's relevant, mineral resource estimation may include material below the selected cutoff grade. This is done to ensure that the mineral resource comprise bodies of mineralization of adequate size and continuity to consider the most appropriate approach to mining. Certain cases with no cutoff use only geological boundary. The grade-tonnage curve that was calculated from block kriging estimates is sometimes different from the actual one, and the kriging should not be used to estimate small block grades from sparse data. So when you create a mathematical model of the deposit and estimate resources using K-mine, you overall increase the reliability of the resource assessment and reduce the risk of decision-making process. Users can also apply cross-validation. So we have two diagrams in the geostatistical task, diagram value estimation and diagram difference value. And you can analyze statistical parameters of the kriging results, such as number of samples, estimation, and kriging variance, regression standard error, and so on. So K-mine also extended its calculation operations. On the block model, you can get reports on volume, tonnage, average grades calculated by different methods like weighted average by volume, weighted average by weight, or arithmetic mean. And users can group the calculation results by any attribute, for example, resource category or rock type, and export them into PDF, Excel, CSV, and XML format file. If you want, you can filter blocks of a block model, and you can use any property for constraints and calculate volume, tonnage, and average grade for the required zone on the main. You can compare operational block model with the previous mineral resource estimates. And sometimes we need to compare block model of the beginning of the year with the end of the year to see the difference, to analyze losses and dilution. And when you create a block model in K-mine, you can conduct an operational feasibility study at any stage of the deposit development, determine the optimal contour of the boundaries of mining operations, justify the most effective options for mining deposits, and so on. You can also proceed with effective planning and design of mining operations and prepare the necessary package of graphic documentation and so on. But the system implements several methods for volume calculation, among them the method of nearest area, the Bolderev polygonal methods, and it's also called polygons of Thiessen. So you have simple grade tonnage calculations using polygonal outlines, and just before constructing influence zones, create graphic objects with calculated thickness parameters or grade values. Using set of Thiessen polygons calculated average thickness, you can calculate zone area and volumes by influence zones. Knowing the value of density, you can also get a report on the resource tonnage. In the calculation result area on the by design boundaries tab, general summary information is displayed on the zones of influence within the entire contour. The by figure tab contains detailed information on each zones of influence. We are clicking on each row and see how the corresponding polygon is highlighted with a marker. And users also can delineate a zone within. In this case, only parts of polygons will take place and will take part in the calculation of volumes and tonnage. We can also compare the volume and tonnage for measured and indicated resources based on the results of the polygonal methods and calculation by the block model. Okay. Okay. So we should not forget to exclude from calculation the number of resources that fall into buffer zones, pillars from rivers or roads and other areas where resources cannot be extracted. So when we create a resource model, we take into account the full set of exploration data and do not forget take into account reasonable prospects for eventual economic extraction. Reasonable prospects for eventual economic extractions implies on an assessment including approximate mining parameters. It's likely to be mined by open pit or underground methods. What's the likely treatment process? The mineral resource estimation is not an inventory of all materials, is drilled and sampled. Realistic inventory of mineralization under assumed and justifiable technical, economic, and development condition in a whole or in part is economically extractable. In situ mineralization, which is marginally economic today, may also become valuable tomorrow. K-Mine provides one digital space where all geologists, mine engineers, and surveyors can work together, exchanging information, receiving real-time data from the site. We offer a solution that allows specialists to change their calculations if there are changes in the mine, where managers and directors can all get up-to-date summary of the situation on the mine at any moment and make a decision faster when it comes to the changes on the site or the market. So today, K-Mine is widely used by companies by different sizes for open pit and underground mining, with over 5,000 surveyors, geologists, mining engineers, designers, and technicians leveraging its solutions on a daily basis. Okay, great. So let's see if we have some questions. I would like to include in this conversation our lead geologist, Tatiana, and our mining engineer, Vitaly, who will answer your questions. So the first question is, what criteria can be used that the block model has been created accurately after block model reconciliation?
There are a lot of different techniques for reconciliation. Reconciliation of resources with grade control, reconciliation of ore reserves, grade control and production, etc. So if we talk about grade control model estimation, some experts claim that normal range of error for accuracy is about 10%. So a significant advantage of reconciling grade control and mineral resource is the ability to produce a total mass balance comparison, including ore, waste, and low-grade mineralization. So I believe that it is not so much the percentage expression of the difference between models that is important, but rather the analysis of the reasons why that led to this difference.
Okay, cool. Thanks, Tanya. Thanks, Anya. And my name is Vitaly, and I'm a head of perspective planning department at K-Mine. And also, I'm in charge of the development of our pit optimizer and scheduling modules. And if somebody wondering the question, what is a miner doing in this interesting stream about geology, I would like to answer this question. Because, it's geology just for geology. I'm sure that this is really exciting, it's interesting, but unfortunately, it's not profitable at all. So geology, it always the base of the basis. It always the start of all of the mining projects. And for sure, the main output from the geology researching activities, it's main input for the next stages of the mine planning. So I would like to ask you a couple of questions to clarify a couple of the situations. So obviously, for strategic planning, we should use the original model that was developed from the geologist and based on the exploration drilling. And that block model, it names it like resource block model. But in this block model, the cubics are really huge, and to continue the planning process, we have to uh, divide these blocks by in a few times with something somehow with some different relationships between these blocks. And for sure, the best way to use an exploration block model.
Exactly. I understand your question. Thank you.
Uh-huh.
And main difference between the ore reserve predictions and the subsequent grade control, mining, and mining components of the reconciliation chain stem from an incorrect understanding of how geostatistical concepts of block size, panel size, and selective mining unit relate to actual mining practices. So when making estimates, in mining applications, we often wish to map the spatial distribution of the mineral attributes on the basis of block support rather than sample support. So selective mining units refers to the minimum support upon which decisions, in particular, or waste allocation decisions in open pit situation. And selective mining units is usually smaller than the sampling grid dimensions. So that's why direct linear estimation of such small blocks has very low precision. And usually we have three methods how to do correct estimation. The first one by two ways. Report at the level of the parent blocks and use a subcell model to calculate parent block proportions, and the second one, report at the elementary level using the estimates migrated from parent blocks. The second method is non-linear geostatistic, like multiple kriging, indicator kriging, disjunctive kriging, and residual indicator kriging, and etc. And the third method, conditional simulation, of course.
Cool. So how do you think could just simple mining engineer just take the block model, divide it by somehow, and try to calculate something without any understanding of what's going on inside this block model?
I think they must try to do that and to improve their skills every day, of course.
Okay, thank you for that. So the next question is should be interesting for the geologist, and it's about the terms of reconciliation. So how often reconciliation between the block model and actual information should be done, and what could be an indicator of the need to do this?
It is recommended to do reconciliation at least once a month based on operational results. It depends on your activity, on your mining works, on your productivity, production target, on your open pit or some mine. An indicator for compulsory and unscheduled verification can be some materiality change. So in the fact from the predicted in the block model. And reconciliations can be carried out on a monthly, quarterly, half-yearly, yearly basis. In this way, the information is accumulated to refine the resource and operational block model.
Okay, thank you. And how do you think, will it have some impact for the resource block model? Should it be updated after this reconciliation?
Yes, it's a very interesting question because an ore reserve is the economically mineable part of a measured and indicated mineral resources. It includes diluting materials and allowances for losses, which may occur when material is mined or extracted. Confidence in the estimate of inferred resource is usually not sufficient to allow the results of the application of technical and economic parameters to be used for detailed planning. For this reason, there is no direct link from inferred resource to ore resource. But there are usually some inferred resources within the mine plan. Sometimes it makes sense to include inferred resources in a mine plan and mine schedule. And sometimes it doesn't make sense to do a separate mine plan for ore reserves, to report ore reserves, and another mine plan to run the mine. So, for example, the JOR code does not stop us using the inferred mineral resources in a mine plan, but it does guide us in how they should be used, these inferred mineral resources, for estimating and reporting ore reserves.
Okay, cool. Thank you. You even predict my next question because I would like to ask, could we use this in our optimization process? Okay, thank you for that. Thank you very much.
Thank you, Vitaly.
I think that's it for today. Thank you so much, everyone who joined in. Don't forget to follow our LinkedIn page, and we'll see you guys again in our next live event. Bye.
Thank you, Anya. Have a
Bye.
nice week. Bye.
Goodbye.